Welcome to Bubble Sort, a simple sorting algorithm. Introduction to Bubble Sort. Bubble sort is a simple sorting algorithm that repeatedly steps through an array, compares adjacent elements, and swaps them if they are in the wrong order. With each pass, the largest unsorted element bubbles to its correct position at the end of the array. This process continues, shrinking the unsorted portion of the array each time until the entire array is sorted. Once a full pass has been completed without sorting any elements, the process is complete and the algorithm terminates. Bubble sort visualization. Here is a demonstration that shows how the bubble sort algorithm organizes a set of numbers. You can see a group of vertical bars, each representing a number, as certain pairs are highlighted and compared one step at a time. When a larger bar appears before a smaller one, they swap places, causing larger values to bubble gradually to the right. As the process continues, each pass through the bars brings the highest remaining value toward its correct position at the end, making the sorting progress clearly visible. This visualization helps illustrate the repetitive nature of bubble sort and makes it easier to grasp how simple comparisons and swaps lead to an ordered sequence. Bubble sort in Python. Now, let's take a look at the Python code for bubble sort. The purpose of this algorithm is to sort a list of numbers in ascending order. It works by repeatedly stepping through the list, comparing adjacent elements, and swapping them if they are in the wrong order. We start by defining the main function called bubble sort, which accepts one parameter, r, representing the array of numbers we want to sort. Immediately, we determine the length of this array and store it in the variable n. This will help us know how many passes we need to make through the array. Next, we enter the first loop, which runs from 0 up to n-it. This outer loop allows us to make multiple passes through the array. Inside this loop, we set a variable named swapped to false. This variable helps us track whether any swaps were made during the current pass. If no swaps occur, we can conclude that the array is sorted and exit early. Now, we move to the inner loop, which is where the actual comparisons and potential swaps happen. This loop runs from 0 up to n minus I minus 1. Here, I is the current pass number. We reduce the range by I because, with each pass, the largest unsorted element bubbles to its correct position at the end of the array, and we no longer need to compare it. Inside this inner loop, we check if the current element, r-tag, is greater than the next element, rg plus 1. If this condition is true, we swap the two elements. We do this by using a Python feature that allows us to swap values in a single line. After a swap, we set swapped to true, indicating that changes were made during this pass. Once we finish the inner loop, we check the value of swapped. If it remains false, it means no swaps occurred, and the array is already sorted. Therefore, we can break out of the outer loop early, saving unnecessary passes. Finally, after all passes are complete, we return the sorted array. In our example usage, we create an array called data, containing a series of unsorted numbers. We then call our bubble sort function with this array and store the sorted result in sorted data. Lastly, we print the sorted array to the console. This completes our walkthrough of the bubble sort algorithm in Python. Pros and cons of bubble sort. Let's look at the advantages and disadvantages of this sorting algorithm. Advantages. First, it's simple and easy to understand. This means you don't need advanced programming skills to figure out how it works, which makes it great for learning about sorting. Next, Because it's an in-place sorting algorithm, it requires very little extra memory. All the sorting happens right inside the original list, so there's no need to create a bunch of new arrays or use up a lot of extra space. It also works well for small lists or lists that are already nearly sorted. If you're dealing with just a few items, or the items are almost in order, this algorithm can get the job done quickly and efficiently. Disadvantages. However, there are some important drawbacks to keep in mind. It's not efficient for large lists. As the list grows, the time it takes to sort increases rapidly. The time complexity is what we call ON squared, or ON2. This means that if you double the size of your list, the sorting time actually gets 4 times longer. So, it's definitely not the best choice for sorting big datasets. Because of this, it's usually not suitable for real-world applications where you have to sort lots of data. In those cases, you'd want to use a faster, more efficient algorithm. So, while this sorting method is perfect for small or simple tasks, it's not the best fit when you need speed and efficiency with large amounts of data. Understanding both the strengths and weaknesses helps you decide when and where to use it. Bubble sort big O complexity. Bubble sort has ON squared time complexity because it uses nested loops. The outer loop runs n times, and for each pass, the inner loop compares adjacent elements up to n times. Multiplying the loops gives roughly n times n equals n squared comparisons. Worst case, ON squared. This happens when the array is in reverse order. Every element must be compared with every other element, resulting in roughly n times n minus 1 divided by 2 comparisons and swaps. Average case, ON squared. For a randomly ordered array, the number of comparisons remains quadratic because elements may need to bubble through the array multiple times. If the array is already sorted, a well-implemented bubble sort can detect that no swaps are needed during a full pass and terminate early, completing the sort in a single pass. Bubble sort is in place, requiring only a constant amount of extra memory. Exam tip: bubble sort's final pass. Warning: don't forget, bubble sort always makes one extra pass through the array. Even if no swaps are needed, the algorithm still completes a final comparison pass to confirm the array is sorted. This final empty pass ensures correctness, especially when optimized with a swapped flag. When answering exam questions, mention or account for this last pass in your explanation or trace. It is a common place where students lose marks by stopping too early.